Hello and welcome to Diplomatic Derivatives. Today we are going to continue with our pure mathematics portion. We have already covered permutation and symmetric groups, and this is part 5 of the series of permutation and symmetric groups, where we have in the previous lecture talked about symmetric group S₄ and the alternating group A₄. So check that video out before we move forward, because there are a lot of concepts I have already covered in all the previous parts. The link is in the description box as well as in the I button above. So make sure you are clear with all those concepts before we move on to this lecture, because here we are also going to perform some exercises. So you need to be clear with the concepts. Moving on, starting with permutation group S₄. So as we have seen in the previous video, we saw S₄. I'll just give you a quick recap. S₄ is made from the set 1, 2, 3. So here S₄ is going to be made from a set of symbol 4, that is 1, 2, 3, 4. Okay, and from those 4 elements we will be making the elements of this group, that is S₄. Okay, it is a group under the product of permutation. For a group, we already know what are the properties that a group must satisfy, for a set must satisfy in order to be called a group. We have covered this in the previous lecture. Make sure to check that out. So S₄ definitely clears all those group axioms and is therefore a group, all right, under the operation of this permutation. So these are all the elements inside S₄. Now you don't need to remember all the elements. For S₄, of course, you need to remember the elements, because the number of elements inside S₄ is 6. But here the number of elements is 24. How do we get the number of elements? We have already seen the formula, which is n factorial. Okay, so from n factorial you get the number of elements inside the symmetric group. So if, for example, you have symmetric group S6, so 6 factorial is the number of elements inside S6. You don't need to remember all the elements or memorize all the elements. Identity is the element, of course, but the rest of the elements are obviously complex, so you don't need to remember them all, but you need to know the number of elements as well as the number of each number of elements of each order. So for order 1, order 2, 3, 4, and so on. Okay, so for that also we need to perform a process through which we'll be able to understand the number of elements of a certain order, okay, which we'll see now. So for S₄, 4 factorial is the number of elements inside S₄. Okay, now we will see how to get the number of elements of each order. Like, we have to know for order 3 what is the number of elements of order 3. From here itself we can directly see that number of elements of order 3, this is 1, 2, 3, 1, 3, 2, 2, 3, 4, 2, 4, 3, 1, 2, 4, 1, 4, 2, 1, 3, 4, and 1, 4, 3 till here. So it's 8 elements, right? But obviously in exam you won't remember all the elements, so you cannot directly state this way, right? But you will be able to do it with the help of a formula, right? We'll see that now. Also, the number of elements of order 4 is 6. The number of elements of order 1 is 1. Number of elements of order 2 is 6 plus 3 is equal to 9. How did we get all of this? We did this process in the previous lecture as well. We'll do it here again. So what do? We take the main thing, which is the number of elements inside the group itself, which is 4 factorial equals to 24. What do? We take 4 and we will write it in how many forms can we write 4? So 4 can be written as 1 plus 1 plus 1 plus 1, 1 plus 1 plus 2, 2 plus 2, 1 plus 3, and 4. These are all the ways in which we can write 4. We can divide 4 and write in this manner, right? So from the first one, we have only 1, right? So from here, you will get the number of elements of order 1. What you do is you perform the formula. Obviously, we know that the number of elements of order 1 is always going to be 1, because identity is the only element of order 1. So that's true for all cases. So no need to perform the formula here. We move on to the next step. We have 1 plus 1 plus 2. Now from here you will get the number of elements of order 2. Also from the next one you will get the number of elements of order 2. Okay, I will explain the difference. So first we will perform the formula on the first step, which is 1 plus 1 plus 2. From here you have 1 and you have 2. So formula is 4 factorial divided by 1 is how many times? 2 times. So it is 1 raised to 2 into 2 factorial. Multiplied, so this is not plus, this is multiplication here, so I wrote that by mistake. It's multiplied. Okay, multiplied by, next is 2. 2 is 1 time, so raised to 1 into 1 factorial. Okay, So you solve it and you get 6. So the number of elements of order 2 from here, from this step, you get 6. From the next step now, 2 plus 2. So 2 is 2 times, so it's going to be 2 raised to 2 into 2 factorial. Obviously 4 factorial divided by this. So you get 3. So from here, from this step, you get the number of elements as 3. So 6 plus 3 is equal to 9. Therefore, the number of elements of order 2 is 9. What is the difference between this and this step? In this one, you're getting these elements. So 1, 2, 1, 3, 1, 4, 2, 3, 2, 4, 3, 4. In the second one, that is 2 plus 2, you are getting the product elements. Okay, that is 1, 2, 3, 4, 1, 3, 2, 4, and 1, 4, 2, 3. And how many elements are these? 3 elements. Okay, so that's how you get this 3. So 6 plus 3 is 9. So the number of elements of order 2 is 9. Similarly, perform for 1 plus 3. So 1 is 1 time 1 into 1 factorial into 3. That is 3 raised to 1 into 1 factorial. You get 8. So number of elements of order 3 is 8. Then similarly, you do for 4 and you will get 6. So now you know that what are the number of elements of each order in the symmetric group S₄. Okay, so remember this, make sure you remember the process. All right, moving on. Now we will talk about the alternating groups. As we talk about the alternating group A3, similarly we're talking about alternating group A4. So from this S4, we will now know what is the number of even permutation and what is the number of odd permutation. Again, we've explained this in detail. I won't be going into specifics again. So we will know what is the number of even permutation, what is the number of odd permutation. For alternating group, we need the number of even permutation. Okay, because only even permutations will make a group. Odd permutations won't make a group. Okay, so the even permutation is 12. And for even permutation, this is the process written for understanding how to get the even permutation. So one element, if the cycle has one element, it's even. If the cycle has 2 elements, it's odd. If the cycle has 3 elements, it's even. If 4 elements, odd. Okay, and similarly, this is two elements, that in case of product, it's even. Okay, so this is the way you get the even and odd permutations, and that's how we got 12 even and 12 odd. So therefore, alternating group A4 is this. So these are the elements that are even permutations. Okay, we got it from the group S4. Okay, now how to understand how to know how many elements are inside the alternating group A4. Again, we have already done the formula, which is n factorial divided by 2. So from that we will get the number of elements inside A4. Also the same way, also here we can check directly. Number of elements of order 3 is 8, number of elements of order 2 is 3, and number of elements of order 1 is 1. Okay, identity is always going to be inside the alternating group, because that's what it's going to make a group, right? Why is the odd permutation not making a group? Because there's no identity. Identity is an even permutation. Identity is not an odd permutation, and without identity, it's not satisfying the group axiom, so odd permutations won't be a group. Okay, therefore alternating group is only for even permutations. So here we get the number of elements of order 1 is 1. That's identity, of course. Number of self-inverse permutation is 3. This we can get from the Cayley's tables. Also from the Cayley table, you can check that which element is its own self-inverse, that is getting identity under the operation. For example, if we have 1, 2, 3 and on the row and 1, 2, 3 in the column, and the product of those two of 1, 2, 3 and 1, 2, 3 is identity, then 1, 2, 3 is a self-inverse. Okay, so here that's how you can check from the Cayley's table. And again, same thing, n factorial divided by 2 is the number of elements of A4, that is 12. So in the exam, if you get any symmetric group, let's suppose you have S6, right? So for 6, they give you S6 and they say how many number of elements are there in its alternating group. So you know the formula, n factorial divided by 2, that is 6 factorial divided by 2, and that's your answer. It can come in MCQs. Okay, so you don't need to worry what are the elements, what is the order of the elements, and blah blah blah. You don't need to think about that. You can directly use the formula and find the answer. All right. So now, since we have been clear about all the concepts inside permutations, we have done all the different parts in which we have explained in detail all the different concepts of permutations. Now we move forward to the questions. In the next video also we will be performing some exercises. We are going to start with the exercise here. So the first question is, express the following permutation as product of disjoint cycles and find the order. Okay, you have to first make a disjoint cycle from the permutation given to you, and then find the order of it. We'll be doing transpositions, we'll be doing inversions and signature as well, so it will be clear for you. Like you'll be able to understand those concepts much better when you perform the exercise here, because these concepts have been explained in the previous video. Now, first question, you have phi is equal to this permutation. From the permutation, how do you make the cycle? So you see the first element, 1 goes to 2, 2 goes to 4, and then 4 goes to 1. So that's one cycle, 1 to 4. Okay, then 3 goes to 5 and 5 goes to 3, so 3, 5. Then 6 goes to 8, 8 goes to 7, 7 goes to 9, and 9 goes to 6. So that's another cycle. Okay, so you have now 3 disjoint cycles. All right, how to find the order of the permutation from the disjoint cycle? Order of the permutation is equal to the LCM of first disjoint cycle. The order of the first disjoint cycle is 3. Then second disjoint cycle, the order is 2. Third disjoint cycle, the order is 4. When you take the LCM of 3, 2, and 4, you get 12. This is the order of this permutation. Okay, that's it. That is LCM of the orders of the disjoint cycles of a particular permutation. Okay, so the order of phi is 12. Now, what are the transpositions? So how do you get the transpositions from the disjoint cycles? It will be 1, 2, 1, 4, 3, 5, 6, 8, 6, 7, and 6, 9. Okay, how many permutation transpositions did we get? 1, 2, 3, 4, 5, and 6. Now, in the video where we explained about the even permutations and odd permutations, there we have explained how do you understand if a particular permutation is even or a particular permutation is odd, right? So this is from where we get it. If the number of transpositions is even, the permutation is even. If the number of transposition is odd, the permutation is odd. Okay, if the order of the permutation is even, the permutation is odd. If the order of the permutation is odd, the permutation is even. Okay, so this is what you need to remember. For transposition, it's the same thing. So if the transposition is even, the permutation is even. That is the case here. Okay, so since there are total 6 transpositions, the permutation is even. Okay, next we talk about inversion. So in the previous sorry, I can't move back. So basically, how do you get inversions? You can check the video where I have explained inversions. So let's suppose you have 1, 2, 3, 4, 5. Okay, don't mind the writing, I'm just making it clear for your easiness. Okay, okay, 3. All right, so if let's suppose you have a permutation given to you, how do you find the inversions from the permutation? First, you look at the first element, 1, and its pair. You're going to make it a pair with 2, let's suppose, right? So for finding inversion, what is the process you do? 1 is less than 2, but the image of 1 is not less than the image of 2. It's greater than the image of 2, right? So 1 and 2 cannot be a permutation. If you look at 3 now, 1 is less than 3. Is the image of 1 greater than the greater than the image of 3? No, it's not true. Let's look for 1 and 4. 1 is less than 4, but the image of 1 is greater than the image of 4. So here 1 and 4 are is one pair of inversion. Okay, you need to remember this. When the number itself is, if 1 is less than 4, their images must be greater than each other. This opposite thing has to happen. Okay, so in that case 1 and 4 will be one pair of inversion. Okay, so in the first question, you will do it for the means. For example, if you're looking at 2 here, now you're going to find the inversion for 2 and the rest of the elements. So 2 with 3, let's suppose 2 is less than 3, but the image of 2 is not greater than the image of 3, right? So it's not an inversion. Let's take 2 and 4. 2 is less than 4, but the image of 2 is greater than the image of 4. So 2 and 4 is one pair of inversion. Okay, that's how you perform this. Again, similarly, 2 and 5 is 2 is less than 5, but the image of 2 is greater than the image of 5. So 2 and 5 is also an inversion. Okay, remember the statement and this way you can do it for the rest of the elements. Apply the same process on this question, and that's how you get these inversions. So you get 1 2 2 4 2 5 3 4 3 5 6 8 6 9, so on. Okay, and the number of inversions of a permutation is called signature. Again, this definition we have done before. Signature is equal to the total number of inversion, which is here 10. Okay, that's how you solve this question. Although these things were not asked, but I just tried to explain it to you through the example, because we have already done definitions of these things, so it's easier for you to understand when we are doing through an example. Question number 2 is permutation is equal to 1 2 3 4 1 2 3 4 5 1 2 3 4 5 element of S5. So the S5 is the permutation. Okay, and in S5 these are the elements. So you've been given a product of disjoint cycles, right? So what you do is, first of all, this you have this the 3 disjoint cycles, right? You will make the product first. So you write the first one, 1 2 3 4 5, and then here 1 goes to 2, 2 goes to 3, 3 goes to 4, and 4 goes to 5. So this is how you write this one. Then the next one, 1 2 3. So 1 2 3 4 5, since it's S5, so obviously it's always going to be 1 2 3 4 5, right? 1 goes to 2, 2 goes to 3, so 3 goes to 1, so the cycle completes. And what about 4 and 5? 4 will go to 4 and 5 will go to 5. Okay, when you find the product of these two permutations, this is what you get: 1 2 3 4 5, 1 3 2 4 5. Okay, after this you take this and find a product with 4 5. So in 4 5, 1 will go to 1, 2 will go to 2, 3 will go to 3, 4 is going to 5, and 5 is going to 4. Now find the product for these two. So you get 1 3 2 4. Okay, so again, product has already been discussed in part 1, so check that out, how to do this. So this is what you get here. Okay, so you get 1 3 2 4. Now from this it's very easy, because this is what we want to get, right? So from here you can get the order. So the order of this permutation is equal to 4 length cycle. Now from this you can get a transposition, so it will be 1 3 1 2 and 1 4. Now since the number of transposition is odd, that is 3 transpositions, so this is an odd permutation. Okay, so this is an odd permutation. All right, so that's all for this video. I hope the concepts are clear. We are done with all the parts, part 1 to 5. Check those videos out for all the concepts related to permutation and symmetric groups. I have tried to cover every single thing in detail, so I hope it's clear. We will be doing more exercises and theorems in the future videos, so stay tuned. Make sure to like, share, and subscribe to my channel. If you have any questions, type them down in the comment box below. If you want me to slow down, I can do that for you as well. So that's all for today. Thank you and bye bye.